Hey friends, here we go, let's do this recording thing again. So remember, take time to take your notes, pause the video, rewind it if you don't understand something that I say, and then take your notes and I grade the notes to make sure you do them. Okay, here we go. Today we are going to talk about arithmetic sequences. What that is another representation of linear functions. This whole unit is about linear functions. We are organizing and keeping under control what a linear function is, and we are analyzing it and analyzing it again and then analyzing it again and analyzing it again. That is what we are doing. Okay, so to dig into it, let's do something that you typically know. So we've done before. So if you want to find the next three numbers in this list, think about it. How do you get from 12 to 17? How do you get from 17 to 21? 21 to 25? Look at that. Do you notice? Add 4 each time. So we get a 29. Add 4. 33. Add 4. 37. Rule. Add 4 each time. Keep it going. Boom. Minus 2. 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 And minus 2. Minus 2 each time. Here we go. Let's do this. Plus 16. 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 All right. All right. So let's dig in arithmetic sequences. That's what we do. These things, these have a special name. We're calling them common difference. Okay, again, what are we doing to this? We are analyzing a different set of arithmetic sequences. Here's the deal with these. We would call this the first term, second term, the third term, the fourth term, the fifth term. Okay, the fifth term. The thing that's interesting about these is that there's nothing like in between the terms. Does that make sense? So if this is the fifth term, there's no like 4.5 term. There's no number that actually gets placed there in the order of these rules. And that's what makes them a little bit different than what we're typically used to for linear functions. Because there is a constant rate of change from one term to the next, these can be modeled with a linear equation. And there are specific number things that are important on this in order to write the equation. So in particular, we have this thing called the common difference. That's also known as the rate of change for us. Rate of change, okay? That's going to be kind of like our rate of change or our slope, we know that by, all right? And then we have things like the first term is a significant discussion. In addition to that, we have something called the closed form of the arithmetic sequence. Is like the formula or the rule that allows us to generate all the terms in the sequence. Okay? And so when we dig into something and we're like, is this an arithmetic sequence? When we have that question, arithmetic sequences are a list of numbers, okay? Like a discrete list of numbers where there is a common difference to get from one to the next. So like, is this a linear or an arithmetic sequence? To answer that question, you have to see if there is a common difference in all of it within the pattern. Okay, you would check. Is that the same? That's plus 2. Plus 2 is the rate of change or the common difference in this consistent. If it is, you would say yes, an arithmetic sequence. And you would say the common difference is 2. So if it is an arithmetic sequence, there will be a common difference between the terms in the pattern. All right. So now when we look at these arithmetic sequences, meaning that there's a constant rate of change between terms that show up in the sequence or in the order of numbers. So if we look at number 1, is there a common difference in this? Is this an arithmetic sequence? Plus 4, plus 4, is that plus 4? Is that plus 4? Yes, it's plus 4 each time. So we would say yes, common difference, or D is what we call it. D is 4. Right? Look at this one. Is there a common difference? -4, -4, -4, -4. Yes, there is. The common difference is -4. Look at this one. Is this an arithmetic sequence? +2, +3, or +2, +6. This is a no because the rate of change between from one value to the next is not consistent. So we would say, nope, not an arithmetic sequence. All right, let's dig into the next one. We have some notation. So if you look at this, 2, 4, 6, 8, who do you appreciate? Mr. Showalter, Mr. Showalter, Mr. Showalter. But besides that, if we look at this very typical arithmetic sequence, we have something, we have a bunch of terms, which we would call A sub n. We would call that the value of the nth term. What is n? N is the term number. So as an example, if we have term number 1, A sub 1, we would say, what is the value of the first term because of that 1? We would say it's 2. That would be the first term. What is right here? What is the value of the second term? It would be 4. What is the value of the third term? 6. Fourth term, 8. Fifth term, 10. What are the values of those terms? Okay. We also have this rule that we can use to help generate the function of, or the equation of, the arithmetic sequence. It's a formula to use. It's a formula for you to find these things and drop them in those specific spots. So, for example, if we look at trying to figure out what the closed form of this arithmetic sequence is, or the rule that generates the arithmetic sequence, we are going to look at the actual listed values. Okay. On this list, we have our first term being 12, okay, which is in our first spot. A sub 1, we would say 12, okay, and remember, n in this is 1. We look at if n is 2 and we're looking for a sub 2, that means we're looking for the second term, the value of the second term, which is 15. If n is 3, we are looking for the value of the third term, a sub 3, being 18, value of the fourth term being 21, okay? D is the notation for the common difference, which is the rate of change between the terms of the sequence. So in this case, to get from 12 to 15, it's +3, +3, meaning the common difference here is +3, friends. Very good. Let's continue. Let's look at using the formula now. So if we want to write the explicit rule for the nth term in the arithmetic sequence, given right there on the right, we would use this formula. And when you're doing it, I want you to write down the actual formula, just like we were doing point slope form. By the way, this is just a really fancy version of point slope form. So A sub n, meaning that's the rule for the arithmetic sequence. A sub 1, meaning the value of the first term, so it's 12, plus we leave n minus 1, and we write in our common difference of d. And this is an equation that we're going to simplify. So we have 12 plus, we're going to distribute, 3n minus 3, simplify again. 3n 12 minus 3 is going to be 9er. So we have our explicit rule, a sub n equals 3n plus 9er, okay? All right, now let's go ahead and try this out. We want to write our explicit rule on it, given these values that we have. So for instance, a sub 1 is 1, a sub 2, 3, a sub 3, 5, a sub 4, 7, d, the common difference between those terms, if you look at it, it's a +2 each time. So we have a common difference of 2. And now when we write the explicit rule, I want you to write down the formula because you're going to need to memorize that. A sub n equals a sub 1, which is the first term, which is 1. N minus 1, we keep the n in there, and then the D is 2. Common difference is 2. Multiply through and simplify that. So 1 plus 2n minus 2. Simplify it one more time, and we get 2n minus 1 for the explicit rule. Let's go ahead and do the next one. Notice this time we have a minus 3 each time, minus 3 each time, minus 3. Okay, again, we're going to have a minus 3. A sub 1, negative 1, A sub 2, negative 4, A sub 3, negative 7. If n is 4, the value of the fourth term is negative 10. In this case, the common difference is negative 3. So A sub n, writing our rule that we're going to use, our formula that we're going to use to generate our explicit rule, we need our A sub 1, which is negative 1, plus n minus 1. We keep that in there, and D being our common difference of negative 3. Distribute and simplify. Negative 1 minus 3n plus 3, because we distributed, and simplify one more time. So we get negative 3n plus 2 when we do the negative 1 plus the 3. And there we go, friends. Okay. So one thing that's interesting on this that you'll have noticed before I finish up here, to keep it short, is that on this, our domain on these is actually restricted to the positive integers, meaning we don't have any numbers other than like the positive whole numbers. So like 1, 2, 3, 4. Because when we're talking about a sequence or a rule or kind of this pattern, we don't talk about the 0th term or the 1.5 term because there's no spots in between. So it's actually this is a function with a restricted domain, which is kind of fun, kind of exciting. So when we go to generate some of these things, like let's look at the next page at number 1 here. If n is 1, A sub 1, using the explicit rule, we're going to take the 1 and put it in for n. Okay, 5 times 1 plus 3, and we get 8. So in this case, in this specific rule, this specific arithmetic sequence, A sub 1 is 0. Let's go ahead and find out what happens when n is 2. So we put n is 2 into the formula. So then we'll get 10 plus 3, or 13. So A sub 2 being 13. Let's continue with the third one. What happens if we want to find the third term in the sequence using the explicit rule? So we substitute 3 in for n, and we put 5 times 3 plus 3, which would be 15 plus 3, or 18, meaning A sub 3 is 18. Okay, we're going to skip this last one, this n sub 4. But what's the common difference on this? You'll notice that you could say, oh, it's plus 5 here, but it's also listed in the same spot that like our slope would be listed if this was like a y equals mx plus b setup. Okay, so let's take a look as well. A sub n, if this is our rule for our for